As I said, we're an analytics consultancy. We're based in the New York, New Jersey area mostly, but we have people all over. I'm based in New York. Serena is actually based in Toronto, which is partly why we're working with the government of Ontario there. As a consultancy, we have expertise in data science, big data, BI, and systems integration. We kind of already had the presenter intros, so I think at this point I'm just going to hand over to Serena. I also just want to say that Serena did basically all of this work. We're both going to be present at the workshop in Boston. But yeah, Serena did this work, and I'll hand over to her now.
Thanks, Daniel. I'm just going to jump into it. A little bit of background about the project. The government of Ontario is interested in leveraging NLP techniques to analyze linguistic patterns in the legislative text and how they can be used to extract meaningful information for the public, as, for example, create links with other legal and not legal documents. For this specific workshop, we're going to focus on the Accessibility for Ontarians with Disability Act and the regulation that comes with it. This is a law that was passed in 2005 and sets out the process for developing and enforcing accessibility standards in Ontario. So the goal of this law is to ensure that all organizations develop policies to prevent and remove barriers for people with disabilities. So as a result, it defines a series of burdens for both public and private institutions. And that's what we're looking at doing today. In this context, a burden is a requirement or an obligation that organizations have to comply with. And in the context of disabilities, that means physical and architectural barriers, but also things that are related to reporting, documentation, and training. And I have the text of the law open here to show some examples. So an example of training requirements is this part of the regulation that's looking at school and educational institutions that are required to provide educators with accessibility awareness, so not just physical requirements. The other example I have here is related to ramps, so some architectural barrier that needs to be addressed. We don't really have the time to go into the details of the implementation, or at least not all the details of the implementation in this webinar, but the code, all the code that I've used and this presentation will be available on our GitHub. So github.com/bardis/ODSC_2009_workshop. So we're going to use a number of well-known libraries in Python, both for NLP and machine learning. But for NLP, we're going to primarily use Spacey, which is a relatively recent open source library written in Python and Cython. It comes with a number of pre-trained neural network models for English, but also other languages, and also supports multi-language models. Now, if you have done any natural language processing in Python, or even if you haven't, you probably have heard of NLTK, which is probably the most popular choice for text analysis in Python. So I'm going to spend a few words just to clarify what are the differences with Spacey and why we're using Spacey as opposed to NLTK. NLTK stands for Natural Language Toolkit, and it's a library that's been developed with teaching and research in mind. So it has a lot of flexibility and a lot of functionalities. On the other hand, Spacey has been developed with performance and production in mind, which means that it does have less functionalities, but it's also very fast and very accurate. So for a full comparison between Spacey and a few other libraries for NLP, including NLTK, I've left a link here. There's a few details on accuracy and speed for several different models. The functionalities that we're interested in for this analysis are sentence and word tokenization, lemmatization, named entity recognition, parts of speech, tagging, and dependency parsing. And we're gonna, these will come out of the box with Spacey, and we're gonna look at a few examples of how we're gonna use this. So first of all, obviously we're importing Spacey. We're also importing Spacey, which is a really nice visualizer that comes with the library. And we're gonna load the English model. So what we have here in this NLP object is really a text processing pipeline, which means whenever we pass it a string, all the models that we've talked about will be automatically applied. Oh, that's what I wanted to do. So I have here an example. I have a sentence that I've stripped out of the outer text. So the ramp must have a minimum clear width of 900 millimeters. So the first thing we're going to look at is tokenization. So Spacey is, we've parsed the sentence with and our Spacey model, and it's correctly recognized that it's only one sentence. What we can do is we can also loop through all the tokens that have been identified in the sentence, and we can get the normalized version, the lemma, so the dictionary form, and then we get a couple of flags. This is saying whether the word is a stop word, and then is-alpha is looking at whether there are only alphabetical characters in the token. These are not the only two flags that are available. There's a few more. I will tell you whether it's punctuation or other flags that can be useful. Next, we have named entity recognition, which is essentially looking at identifying named entity mentions in the sentence and classifying them into predefined categories. These are generally things like proper nouns, organizations, locations, dates. So if we access ents, which is the property where all the named entities are saved, we can see that we have 900, and using Spacey, we can render the sentence nicely and highlight the 900, and will also tell us what type of entity we have here. In this case, it's a number. Next, we're going to look at parts of speech tagging and dependency parsing. These two models are somewhat related. Parts of speech tagging looks at assigning words with similar grammatical properties to the same tag or category. These are your parts of speech. And then dependency parsing looks at building a tree that represents the grammatical relationships between words and sentences. So again, there will be a few tags attached to the tokens, and they're slightly different. So if you look at ramp, it's a noun, and it would be then a noun subject for the dependency parsing tree. Mustn't have both verbs, but have different grammatical function, where have is the root of a sentence and must is just an auxiliary. And again, Spacey comes with this really nice visualizer, so you can look at the tags that have been assigned to the single words and what the tree looks like. So the arrow will represent a parent-child relationship. So before jumping into the analysis, I want to do a little grammar review. We're going to use this concepts later on, so it's important to know what we're talking about. We're going to talk about subject and object. So a subject in grammar is the word or phrase that indicates who or what performs the action in the sentence. So in the context of burdens, this is going to be the entities that are responsible for complying with the burdens or the obligations. In the example that I have here, every employer is the subject of the sentence. So it's not just a noun, it's a couple of words, and that's who's responsible for complying with this burden. The object, on the other hand, is the entity that is used, that is acted upon by the subject from a grammar standpoint. What that means in the context of burdens is the burden specification. So in this sentence, it would be providing individualized workplace emergency response information, which is the entire object of the burden. So going into the analysis, our first task is going to be identifying the burdens. Because the structure of legal text is relatively rigid and the lexicon is relatively limited, we're going to use a rule-based extraction method, and we're going to build a lightweight ontology to do so. This lightweight ontology will be a series of verbs that we expect are going to point us to obligations. And so we have a short list here, and we're going to use WordNet to expand on it and to make it more exhaustive. WordNet is a large lexical database of English. So each word is grouped into a set of cognitive synonyms, which are called synsets. So each of these will express a particular concept, and they will also be linked by conceptual, semantic, and lexical relationships. So this creates a network of related words and concepts that it can be navigated via an interface online or can be downloaded. We are going to access it using the NLTK functionality. This is one of those examples where NLTK offers this feature and Spacey doesn't. So it's really easy to just look up all the synsets of a word this way. So to build our list of synonyms, we're just going to loop through the ones that the verbs that we already defined are part of the ontology, and we're going to add all the synonyms. So we get a little bit of a longer list. So at this point, we're going to use this list of verbs to identify the obligations prescribed by the statute. So given a sentence, we'll look through each term, and we'll extract the lemmas, so the dictionary form. And if any of those lemmas appears in the list of verbs we're constructed, then we'll add the sentence to the list of burdens. So this is our input. In this data frame, every record represents a different sentence that's being parsed from the original text. And then we'll just loop through and add this flag for whether we think it's a burden or not. Now, for the sake of evaluation, we have attached a ground truth to each sentence. However, this hasn't been done by anyone with a strong legal background. So we'll just use it to eyeball what the results, how accurate we are with our results. We found 543 burdens, and we have an accuracy of 89%, roughly. So for about 89% of the sentences have been correctly classified either as burden or not. We're also going to look at precision here. In this sentence, TP stands for, in this formula, TP stands for true positive. FP stands for false positive. So what we want to look at here is how many of the sentences that we've tagged as burdens were actually real burdens, and we have a 76% here. So we'll look at some of the an example of a burden that was misclassified. And we can see that it is actually a requirement. It's just not considered a burden at this point because it is describing some obligation, but it doesn't really constitute a burden on the organization. We're also going to look at recall. So of the burdens that we have in the text, how many we're actually correctly labeling, and we have a 97%. And the ones that we're missing, here's an example. There is actually no verb that points at an obligation, but we have is responsible, which clearly defines a burden for the minister in this case, but doesn't really show up in our verb list. So at this point, what we want to do is understand who's responsible for these burdens. And so this is where we're going to extract the subjects of the sentences. And we're going to try and use them to organize the burdens into homogeneous groups based on the entities that they affect. So in particular, we want to see if we can split them between public versus private, where by public we mean the government or its agencies, and private includes companies and so businesses and individuals. For this part of the analysis, we're going to use dependency parsing. And I have here a list of tags that point at subjects of the sentences. I have here an example because, like I mentioned before, the subject can be composed by more than one word, and that's the case with the sentence. What we want is all of these words to be tagged as subjects. However, this is what happens with using dependency parsing. So we only get organizations, and if we look at the tree, we do have the organization connected to keep, which is the verb, by a relationship, and organization itself is connected to the other words, just not by this end subject tag. So the solution to these is to combine the dependency parsing tags with breadth-first search, which is an algorithm for navigating graphs and trees. And we're going to use it to navigate the dependency tree, starting from the subject to identify all the subset of all the tokens that are connected to the subject by a parent-child relationship. So I'm going to use a few helper functions here that will be available on GitHub. And I'm just going to create a data frame where I have still have the sentences, but also have split them into subject, object, and a verb. So in order to proceed with the analysis, we're going to do a few things. We're going to normalize the subject, so the subject string. We're going to project the normalized string into a semantic space using Glove. We're going to use Glove, which is the model for word embeddings published by the Stanford NLP group, which is available online in various forms. And we're going to use the 50-dimensional vectors for this reason. We're then going to run some dimensionality reduction, and finally we're going to try and cluster them using k-means. So first of all, the normalization, we're just stripping out all the stop words and just keeping words that are tokens that are composed by alphabetical characters. Then we're loading the vectors, the word vectors, and we are projecting the normalized string into the Glove space. What we have now is the same data frame, but we have added 50 columns. Those 50 numbers represent the Glove vectors. What that means in terms of representation is we've essentially projected the subjects into a semantic space, which means words with similar meaning will be close to each other in distance in this space. For dimensionality reduction, we're going to use spectral embeddings. These are nonlinear embeddings that use a spectral decomposition of the graph Laplacian to find the low-dimensional representation of the data. That means that points that are close to each other on the manifolds are mapped close to each other in a low-dimensional space. And we're just leveraging scikit-learn for this. We're projecting into 2 dimensions. And we're then running k-means and using the elbow method to figure out how many groups we can create from here. So it looks like going from 3 to 4 groups doesn't really come with enough improvement from an inertial standpoint. So we're going to run k-means on 3 groups. And this is what comes out of it. So this is the points represents the projection of the subject vectors into the two-dimensional space. And it looks like the three clusters work pretty well. We have these three pointy shapes going out in opposite directions from the center of the plot. But really, to understand whether this makes sense to us and whether it's actually helpful, we want to look at the single groups and visualize them in a way. So we're going to look at the distribution of frequencies in the group, and to do so, we'll just quickly transform the strings into a matrix of word occurrences, and then we're going to look at the aggregate frequencies at a group level and rank them. This graph is showing the top 5 words in each group. And we can see that there's almost no overlapping. Really, the only overlapping happens around provider. So at least at this level, we're pretty happy. It seems to be working in a way that makes sense. Let's look at the single groups now. We're going to look now at the top 15 words in each group. And what we have in the first group is service, transportation, and provider, which are by far the most popular words. And then we have words like vehicle, mobility, we have rail, which make a lot of sense in the context of accessibility. This is so 20%, about 21% of the burdens that we have identified fall into this group. And we can also see that they largely come from this transportation standard section in the text, in the original text. So this kind of makes sense. The second group is a little hard to read. Organization is by far has by far the highest frequency. And then there are a mix of references to public and private. So we have minister over here, public itself over here. So there are some references to the public. And then we have employer, we have person, we have provider and director, which probably refer more to private. So it's kind of hard to make up this group. And it's actually 50% of the data. And it also comes from several different sections. So kind of hard to read. For group 2, for the last group, this seems to be dominated by physical requirements. So we have ramps, surfaces, we have handrails, trails, slope, all of these words that refer to architectural and physical standards. This is about 25% of the burdens, and it's largely coming from the design of public spaces standards, which is a pretty important section of the text. So what have we learned so far? We know that AUDA has a significant section dedicated to transportation services, and that was about 21%. And we can't really split them between public and private. There's no difference between the two. We then have about 25% references to architectural and physical requirements, which also makes sense when we think about accessibility. We're probably the first thing that comes to mind is about physical barriers, so that makes sense. And then for the rest, we're finding that it's hard to split between responsibilities that fall on the government and its agencies and responsibilities that fall on businesses. So what we can do at this point is try a different approach. And we tested topic analysis using latent dataset allocation. This is a generative model that explains how the words have been assigned to the documents, which in this cases are the sentences or the subjects. And it does so by identifying latent variables that explain regularities in the text, and that's what we call topics. So we're running the scikit-learn version of the model again, and we're using this PyLDA viz library that makes some really nice visualizations. And I'm going to jump onto the notebook to show this. So this is the result of the visualization. What it's doing is it's projecting the topics into a two-dimensional space, so we can look at it this way. The distance between on the graph is proportional to the distance in of the vectors from each other. We can see again that we have service provider dominating one of these groups. If we hover over the words, we can see where they are present, and so again, they're pretty, this group is pretty heavy on them. There's almost no occurrence of these words in the other two groups. Group number 2, again, dominated by organization. We have some of the words that we had before, but also some others that we hadn't seen this high, at least this high before. And then finally, the third group, it's a little bit more mixed. It does show that has the government, has references to physical objects again, but it doesn't seem as neat as the other one. So we do get similar results, and we could play around with the number of topics and see how that changes the analysis or the results of it. But what we get is that some groups will be cleaner, and but it's still kind of hard to see a distinction between the groups. So as a follow-up, and that's what we're going to be looking at in our workshop, together we're going into more details in how we've gone about the analysis, is we can think about being a little bit more clever in terms of pre-processing. So we could think about extending the list of stop words, for example, and include things like organizations and other words that are used extensively in the original text, but don't really tell us, don't really give us a reference and don't really give us a lot of information in terms of splitting between public and private. The other thing that we can do is look at the objects of the sentences. So what is whether there are patterns in the specification of the obligation. And I think that concludes it for today. Again, this is the link to the GitHub. Thank you to everyone that joined us today.
Thank you everyone for joining this webinar.